Now let's develop a composite formula for Simpson's rule. Let's start by applying Simpson's rule to two subdivisions of the interval AB. Here's the interval AB, and we've split it into two. H is b minus a over 2, so the first width is h and the second width is h. Apply Simpson's rule to the two individual regions and add them, and let that denote the composite two-subdivision Simpson's formula. Here it is. The two-subdivision Simpson formula for the integral of f from a to b is the one-division Simpson formula for f from a to a plus b over 2, as well as the one-division Simpson formula for f from a plus b over 2 to b. Focus on the first term. Remember that Simpson's formula involves three function evaluations, the two endpoints, a and a plus b over 2, as well as the middle point. The second formula also involves 3 points. The two endpoints, a plus b over 2, which is already marked and already been evaluated, as well as the endpoint at b, and then the middle as well. Writing those down explicitly gives the following formula. The first one is Simpson's formula for the first subdivision, and the second one is Simpson's formula for the second subdivision. Notice the one common function evaluation at a plus h. Combining those gives the following expression. This is the two-subdivision Simpson approximation to the integral from a to b. Notice that two subdivisions leads to 5 function evaluations. And there's also a pattern inside of 1, 4, 2, 4, 1 for the weights. The 4s are coming from the intermediate point in Simpson's formula always has a 4. The 2 is coming from the middle point, a plus b over 2. Its function evaluation is included in both integrals. Therefore, when terms are collected, it has a weight of 2. Now, it's straightforward to generalize this to k subdivisions. Here's the interval a to b broken up into k subdivisions. H is defined, as usual, as b minus a over k, so it's the width of each subinterval. And we'll use the same idea. The k subdivision Simpson's approximation to the integral of f from a to b is simply the sum of all the individual one-division Simpson approximations of these integrals on each interval, a to a plus h to a plus 2h, and so on, all the way up to the last one that ends at b. You can just formally write that as a sum. Notice that the index I goes from 1 to k, and each interval here is of width h, starting at I equal 1 at a and ending when I equals k at b. As we've already seen, some of the function evaluations are used in two of these Simpson approximations, the two regions for which that point is a member of. Consequently, if you count, k subdivisions results in 2k plus 1 function evaluations. We'll go over how they're all combined in just a moment. Let's do an error analysis. Remember that for Simpsons, the error bound in each subdivision is m4, where m4 is an upper bound on the fourth derivative of f over the interval a to b, times h to the fifth over 180. In this case, there are k subdivisions, and h is therefore b minus a over k. Now the integrals of the subdivisions add to produce the integral from a to b, and therefore the error bounds should add too. The worst case error is just a sum of all the worst case errors that occur in each subdivision. In this case, it's k times this individual error. So the overall error bound is k, m4, h to the fifth over 180. Make a substitution for what h is, and then finally cancel one of the k's, resulting in this final bound that says the error in doing a k subdivision Simpson's rule is decreasing at the fourth power of k. Let's go over a little bit how the points are combined. Again, we'll have a 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1 pattern. The number of 2's and 4's in the middle depend on the number of subdivisions. Let's count them up though carefully. So here I'll use the index of the function evaluations, and we'll look here as well as over on the diagram to see what we're talking about. The very first function evaluation gets a weight of 1, and that is the function evaluation at point A. The second function evaluation, gets a weight of 4, and that is the second point there between A and A plus H. The third function evaluation point gets a weight of 2, and that is at A plus H. This repeats 4, 2, 4, 2, 4, 2. Finally, we end up over at the last interval, which is the 2k minus 1th function evaluation. That gets a weight of 2. That's right there. Then the 2kth function evaluation gets a weight of 4, and that's the second to last point. And finally, the 2k plus 1th function evaluation, which is at B, gets a weight of 1, and that is right there. Let's go try this out in MATLAB on the same example that we did using the composite trapezoid formula. Here we are in MATLAB. We'll follow the same procedure that we did for the trapezoid example. The number of subdivisions will vary from 3 to 99. We'll bookkeep the error. We'll be able to know the error because we do know in this example what the true value of the integral is. As we loop through all the possible subdivision values, we take on a subdivision. Remember, for Simpsons, the number of evaluation points is 2 times the number of subdivisions plus 1. We'll also make up the weight vector. This consists of 1's at the endpoints, 4's at some of the points, and the value of 2 at other points. You can look and see how I'm making this up and see if you agree that I've got the pattern right. 1, 4, 2, 4, 2, 4, 2, 4, 1. X is linearly spaced from 0 to the limit. This is from A to B with the number of points that we defined. H is B minus A, which is pi over 2 divided by K. And finally, F is sine of X. Remember, X is a row vector, so therefore F will be a row vector. The Simpson approximation is simply H over 6 times the weighted sum of the function values. I'm doing that with a dot multiply and a sum. And then the error is the absolute value between the true value, which we know to be 1, and the Simpson approximation. Then we'll plot a log-log plot of this, the error versus the number of subdivisions, and plot that. What we'll note is that the slope is approximately about -4, which is consistent with the k to the 4th in the denominator on the error bound for composite Simpson. Let's do it. There it is. Subdivisions across the bottom, absolute error on the side. And let's track a factor of 10 increase in subdivisions. A factor of 10 increase in subdivisions is going from here to here, from 10 to 100. And in doing so, what happens to the error? It goes down a factor of 10, 100, 1,000, and nearly 10,000. So we have a 4-to-1 slope here on a log-log plot, which, as I mentioned, is indicative of the k to the 4th in the denominator of the error bound for Simpson's approximation.